Okie dokie. How excited are we? We're going to do an actual one of these regression thingies in Excel. Ooh, just kind of makes you tingle, yes? So, what I have is actual data here on a series of years and how many visitors come to Las Vegas. Now, you notice I put the years in as 1, 2, 3, 4, 5, 6, 7. That's a whole lot easier than this year. That year right there, which is 2012, it is much easier to put in 12 than it is to put in 2012. So usually when we have years, we start with, well, that's 2001 and that's 2002. And you with me? It's way easier to do it that way than it is to put in 2012. It's much easier to put in the number 12. You got that? Does that make sense? Okay. So very rare that we put in, 1952. We're more likely to put in 52 or to put in 1 if that's when our data starts. We want to put in some smaller number for the year, right? So think of this as 2001, 2002, 2003, 2004, 2005, 2006, 2007. Okay? Everybody with me on this? I also have a year down here, which is 2013. I'm going to leave it out. And why am I going to leave it out? I'm going to calculate these, and then I'm going to create a regression equation. And I'm going to put these numbers into that regression equation and see how well it actually works. See if it'll predict that number. I should put 13 into the regression equation I calculate, and I'll get that number. Okay? So remember here that A, the year, is X, and the visitors is Y. A is independent, the year. Visitors is dependent on the year. Okay? So I take my Excel, I click on the word data up here. See data, not the Star Trek guy. And over here it says data analysis. Tools for financial and scientific data analysis. So let's click. And a box opens. And look, there's all our old friends like correlation and covariance, descriptive statistics, regression, our new friend. Look, it even does t-tests. Regression. We click OK. OK. It says, I need your Y and I need your X. Well, let's click. This is Y. So we highlight it and we hit Enter. And it fills it in. And then it says click on here, and we do that. Now, labels. Notice that the first line here is words, not numbers. So we click labels. Notice it's going to do a test at 95%. That's good. Yes, we understand 95%. We can make A equal to 0. Don't ever do that. Then it says, where do you want your output? And you can put it in a new worksheet ply. You can put it in a new workbook. You can put it in a spot. Okay? We'll go ahead and put it in a new worksheet ply just for fun. Then it comes down here and it uses the word residuals. Most statisticians really don't talk about their residuals so much as the errors. Those are the errors. So let's click on the error residuals, which is the errors. And let's click on residual plots, which is another way of saying it's going to graph the errors. Okay? With me on that. Can we click OK? You ready? It'll be exciting. All right. So, again, they must have had somebody who's not a statistician to do this, and they really didn't know what they're doing. You have to get the lines. You have to move stuff around to make the lines big enough so that you can read what it says. But we'll survive. Okay. So, let's start up here. It says summary output and then basic statistics. It says multiple R. That's little r. It's 0.95. The biggest it could be is 1. That's good. R square. See R square. 0.9148. What does that mean? It means that 91.5% of the variation in visitors is explained by the year. In other words, that looks really good, yes? That's the highest that could be would be 1, and it's pretty close to 1. Okay? We have this thing called adjusted R-square. We don't really need to worry about that yet. It's adjusted for our old friend degrees of freedom. The important thing is those two should be close, and they're pretty close. The standard error is 1. Okay? The standard error is the average error. Now let's go back to our sheet 1 here for a second. Notice the visitor says 29.6. That's not 29 visitors. That's 29 million visitors. All right? 30 million visitors, 30 million, 33 million, 35 million. So when this says the standard error is 1.02, that means the average error in this regression equation is 1,021,862 visitors. It's off by 1 million visitors a year. Good or bad? I'd say not really that exciting, right? If we're going to get our number wrong by 1 million people, that's a lot of people. But part of the problem with this, of course, is we only have 12 observations. That number is way too low. We should have 1,200 observations, but Las Vegas hasn't been around 1,200 years. So it's a little hard to do. Okay? So we have this table called ANOVA. That's analysis of variance. We're kind of going to skip that for now. Eventually, we're going to do a regression where we have more than one X at the same time, something called multiple regression, where we do multiple X's. Then that table becomes really important for us, and then it has degrees of freedom. And the interesting thing that we might want to know is the variation. So we have total variation, explained variation, which it calls regression, and the unexplained variation, which it calls residual. So the thing we just did back before where we were calculating, had that little graph and we were calculating in the other video, that's that calculation for you if you really wanted to do it. So for example, R square here is equal to 112.25 divided by 122.7. The explained divided by the total. Okay? So, more fun. Let's go down here to this line. All right? There's some stuff down here. This part, guess what I'm going to do? I'm just going to delete that because I don't care about that. We have intercept and year. That's A and B. A and B. So we have these coefficients here. That's A, that's B. Do we got that? That's A, that's B. So we're going to write out a regression equation that says y equals A plus B. Okay? Or visitors equals 29.24 plus 0.88 times year. Okay? What's that mean? Well, it's got one really important thing right here, that's 0.88. That means each year we expect the number of tourists to go up by 0.88. And since this is in millions, we expect the number of tourists to go up every year by 880,000. Now, that's a testable prediction, and that's maybe a useful prediction. If it's good, if it's 91.5%, that's pretty good. If we can say to the Las Vegas Convention and Visitor Authority, dudes, there's going to be 880,000 more people coming here every year, that's useful information for them. Okay? Now, we have a way to test and see if this is any good. And the way we do that is to test and see if B equals 0. So here's B, right? B, we need to test and see if B equals 0. How do we do that? We know that T equals, all right, X bar minus mu. Remember this? And Where's my math? X bar. X bar minus mu. I know you're thinking, why didn't you get those out? Well, you know how life goes. S divided by S. We just did this before, right? This is what we were doing in chapter 8. We did this like all year in chapter 8. So now we have, in our case, we're going to put in B minus 0, which is kind of a waste, divided by some S, some standard deviation, some standard error. So B minus 0 over the standard error, actually. Put an X in there. Okay. So if I look here, look, I have the standard error. Remember standard error? You're like, I do, vaguely, somewhere in the back of my head, I remember that. So this is B. B minus 0 is just B. I'm going to take this, divide it by its standard error, right? B minus 0 is just B. So I'm going to take B divided by the standard error. Okay. Come back over here. B divided by the standard error, I get a T of 10.3. So my T equals 10.3. Now what you would do is find a critical value. Okay. And how many degrees of freedom do you have? Well, you got 11. Actually, you have 10. Why do you have 10? Because you have two variables. You have X and you have Y. Because you have two variables, you have 12 years of data. 12 minus your two variables. 12 minus 2 is 10. We could go look that up in the T table, right? You're thinking to yourself, ugh, I don't want to look this up in the T table. And I'm saying to you, what is more fun than looking things up in the T table? You have 10 degrees of freedom, one tail 0.05, 1812. So let's go back. Our critical value is 1.812. Our T is greater than our critical value. Therefore, what do? We reject H naught. What is H naught? H naught is that B equals 0 or no relationship. What did we do? We rejected that. Is that a good thing? Yes. By rejecting that 10, it tells us that there is, in fact, a relationship between X and Y, between year and number of visitors, because this T is big. The other way to look at that is what we call the p-value. Remember p-value? P-value is the probability that hypothesis, right? The probability associated with that hypothesis, the probability that is true. Well, the answer is the probability is 1.4 e to the 0.6. What does e to the 0.6 mean? It means we're going to move the decimal point 6 spots over. So there's 1. See how it says 1? 1. That's the p-value, right? Which is, it's really 1 times 10 to the minus 6 power, right? And we can make that minus 6 power because we know what we're doing. Okay, that's what that is. That 1.14 e to the minus 0.6 is that which is that. For this to be reject, it's got to be, that p-value has to be less than 0.05. So 0.05 is greater than that, right? Therefore, we reject H naught. Okay, so these two are the same thing. We don't ever actually have to look, because the Excel does this for us, we don't ever have to actually look our value up in the t-table. We did that t-table thing just because we felt like it, because we're happy doing t-tables, but we didn't really have to do it. And here we get 1.14. In other words, because that p-value is less than 0.05, the statistics are telling us that this is a valid regression. Okay, it's a valid regression because the p-value is less than 0.05, or the t-stat is good. Now, the other interesting little piece of news here is that this uses something called an F distribution. Ooh, you're thinking, doesn't have anything to do with my grade, does it? And no, F is for our old friend Fisher, if you remember him from back at the beginning of time. The point here is that F and T we've been using, F we haven't used yet, but F and T are related. If I take this 10.3 right there and I square it, I get 107.5059. The F is the square of T. T squared equals F. Got that? T squared equals F. Squared. That's a squared. Okay? T squared equals F. Are we good? Pretty exciting, yes? This is all just really exciting stuff. Okay, so now all that looked good, like our regression's really good, except that our regression isn't really good. Why is our regression really not really good? The answer is, for regression to be good, the errors have to be a certain way, right? The errors have to be small, and they have to be random. Well, we drew a graph of the errors, and the errors go nee, nee, doo, doo, doo. This is not random. This is up and down and up and down. There's a pattern in these errors, is there not? The error should be in there with no discernible pattern, but these errors have a very clear pattern. And what that tells us is that this regression really isn't good. It's pretending to be good. It's hidden. And you're saying, what it means here is that there's a pattern in the errors. Our square includes not only the information it got from year, but that our square includes the pattern that's in the errors. So it's lying to us about how good this regression is. If we could figure out what's causing that pattern in the errors and put that into the regression, then life would be good. But because there's a pattern in the errors, our square is saying, hey, we can explain number of visitors who come to town, but we're explaining it with both the year and whatever's messing with our errors. But we don't know what's messing with our errors. So this R-squared tells, in this case, the R-squared says, hey, we could do a good job of explaining the number of visitors every year, but this pattern in the errors says we're not doing a good job because we're missing it. Okay? So one last thing to do, and that's this. So what we want to do is put 13 into our equation. So come over here. Here's our equation. In place of the year, we want to use year number 13. Okay? Can we do that? Year number 13. Now we have to do a little exciting math. We have to multiply 13 times 0.88 and then add 29.24. And fortunately, we have a computer. So we can come right here and we can say that needs to equal B17 plus B18 times 13. That's our regression equation. Yes, everybody agree? 29.24, that's A, that's B, and that's 13. I hit enter, and I get 40.76. So our regression says that in year 13, 40,759,000 people should have come to Las Vegas. And how many did? 37 million. The regression says 40 million should have come, 37 million should have come. That's off by 3 million people. That's a lot of people. And again, why isn't it good? It's not good because there's something going on over here, and we're not taking this thing over here into account. So this says we're really good, but we're not really good because there's something going on here that we're missing. Okay? We're excited by this. It's very exciting, yes. Okay.